Our speaker today, Chandrajit Bajaj from UT Austin, where he's a professor of computer science and director of the Center of Computational Visualization. He also holds the chair, Applied Mathematics Chair in Visualization there. When you look at Chandrajit's CV, one of the most impressive things that strikes you right away is very high H index, 56. Enormous number of citations. He works in many different fields. Today he will talk about automated prediction of molecular assemblies with quantified uncertainty. And I should say that these things are inherently difficult to predict, inherently uncertain. So the fact that you can quantify this uncertainty is even more impressive. And with this, the floor goes to Chandrajit.
Thank you. And I hope I can hear myself, but I hope everyone can hear me too. Thank you for the invite. I'm here actually also to attend a dissertation defense of Professor Alexei's. And so, my first time to Blacksburg, everything has been super impressive. Wonderful state, of course, and the fact that the amount of computational biology and bioinformatics that's happening here is something that I'm going to take away with. So this talk today also is somewhat related. It's a little focused on structural biology aspects and also on prediction. I show my formative roots as a person from computer science and somewhat in math. So I'll try to make it as clear to those who are the biologists in the audience and as well as those who are the computer science in the audience. So the problem is of predicting molecular assemblies, and a special case of molecular assemblies are these capsid shells which have spherical symmetry. And these are, for those who are perhaps have recognized them, are like virus capsid shells, and the genome of the virus is housed within them. This is joint work with my PhD student, Mohibur Rashid, who's finishing off in the next few months or so. And it's been a nice exercise where not only was the problem studied from a biological aspect, but as we examined it from a computer science aspect, you're always encountering new mathematics that you don't know, and that's always been the hallmark of my entire work. I find things problems exciting when I can always go back and jump into stuff I don't know, which I don't know a lot of. But I can learn some new mathematics and then bring it back into computer science. So, basically, actual problem solving. So, assemblies comes about in many a way, and I'm trying to find the right position to hold myself because I'm trying to stare at the screen, but I'll probably stand here and I can see what's happening here and also point to the screen. So 2D jigsaw puzzles, I guess many of us have grown up with and also have observed various types of tilings and other kinds of multi-layered 2D puzzles. And this is, of course, a special case of the 3D puzzle problem. So the 3D jigsaw puzzle problems have been used in architecture to come up with tile nodes. Also, it's about in reconstructive archaeology or even in assembling fractured pieces with the most precious object that you've destroyed and you have to put it back together. You can start to see the combinatorial nature of the entire exercise. Not only do parts have to fit together, but exactly what combinations of parts have to fit together is part of the same thing that we had to worry about in 2D jigsaw puzzle. And as humans, of course, we train ourselves and we can quickly put very complicated things back together. But as we'll see today, we're solving some very computationally hard problems. They're called NP-hard or sometimes p-space hard problems. And how do we do that on a computer then becomes a big challenge. Can we do them in polynomial time as opposed to exponential time, trying every possible combination? Of course, this would be with some error, then how do we bound the error? So that's the main essence of this entire problem. In the molecular world, where this is also very apparent, multimolecular models exist all the time. Just because multiple proteins or RNA or other molecules come together to perform a certain activity in a certain process. And there's this other notion of spontaneous assembly. So viruses, in their life cycle are infecting a host and, of course, injecting their genome into the host. And then, after all, when it goes back and creates its new virion, it spontaneously assembles a shell which houses its genome and then buds out of that cell. And these shells or nucleocapsids are often made up of proteins. And a single protein, sometimes 2 or 3 proteins. But it uses symmetry to encode this entire container, which is much larger than, of course, sufficient enough to house its genome. So typical viruses are on the order of 100 nanometers in diameter. And the fact that it hadn't been for symmetry, they would have to have a lot of encoding of all the constituent tiles of the proteins it would need to build its shell. So the fact that it can encode a single protein and then make multiple copies of it to build larger container shells is part of the evolutionary surprises that we see often in life. So these are the kinds of problems that we are interested in. So to get into the methods that we tend to use, one of the things that we've been doing is developing different types of molecular models. And these are models which are approximation of the biochemical, biophysical, and also, in some sense, quote unquote, the geometry of a molecular system. And so molecules, especially biomolecules, live in water, and so a large part of the community explicitly models of water as well. Water, as you know, H2O is the cartoon shape of Mickey Mouse is pretty relevant because if you look at the charge density distributions, they are roughly like a large oxygen with 2 little hydrogens, as Mickey Mouse ears stuck on. And so when you're looking at molecular systems with, say, 5,000 to 10,000 number of atoms, you suddenly realize that the number of waters that you need can go in the billions. And so clearly as a computational person you say, oh, what is my input size? The input size that I was interested in studying was only, say, the order of 10,000 atoms system, but I already have made my input size to be 1 billion just because I've had to add all these bits of water. So that's where, computer scientists as well as computational scientists have said, well, let's just go back and come up with an approximation, and this approximation is called an implicit homogenization. So you take all of the water molecules, 1 billion of them, and think of them as a continuum. And this continuum is then, there's an interface that separates the continuum from the charge distribution or the electron distribution of the molecule or the system that you're going to consider. And so that interface that separates the electron distribution of this union of atoms of your molecular system from the continuum, which is water, is called the molecular surface. And such calculations are an approximation. We were already working with one approximation in the explicit sense, here's working with another approximation also. And this is so that one can start dealing with multi-protein or even pairwise protein interactions and coming up with some error-bounded way of making some prediction. Otherwise, you are constantly, impacted by the sheer amount of water that you have to be dealing with while you're only studying how does one molecule interact with another molecule, what is the binding footprint of that interaction, and so on. So in the rest of the talk, I've been usually making this approximation, and with this approximation, I'll be telling you of some of the techniques and the problems and challenges that we've been facing, as well as some of the solutions we've come up with. So with this model approximation, the 3D assembly prediction problem then can be formalized in this following way. You say, suppose I had a bunch of molecular models or components, M1 to Mn, And let me consider T to be the space of rigid and flexible transformations available to each component. Then this complex that I'm trying to predict is nothing more than the transformation that maps each model under this transformation, and the union of that is what I want to go back and predict. But since I'm doing this computationally, I must have a scoring function that predicts how good is my prediction from the true solution. So this scoring function I call F. So the assembly prediction problem is reduced to something called a non-convex geometric optimization. I should have mentioned, and I kind of skipped in the beginning, many people in computational biology, especially working with structure, rely on this amazing growth in the last decade or so of something called molecular dynamics. And molecular dynamics models are very good and getting better. And so a lot of the assembly problems can also be solved, or prediction problems of molecular complexes can also be solved by molecular dynamics approaches. The bane in molecular dynamics is that you have to tie up lots of supercomputers as the size of the input increases. So you're working with a 10,000 atom system. The best you can do nowadays routinely is about several, say, microseconds. And I say the best, you can use the best of hardware and you might get a millisecond of simulation. And so if the quantity of interest that you're trying to predict, and if these complexes are going to be formed within that millisecond, yes, you can predict it. But there's always been this other group, the one that I kind of I belong to and I'm promoting, is saying, is there other solution ways that we can come up with that can solve the problem? And the way that I've been working on is using geometric optimization. And it's an exhaustive approach, but I'm into speeding things up, because that's where the computer science in me comes in. So instead of doing this as a molecular dynamics prediction, I'm doing it as a non-convex geometric optimization. So I'm going to search for all possible combinations and all possible configurations. And this high-dimensional search, I'm going to first characterize, and then I'm going to say, I'm going to sample this uniformly. And when I sample this uniformly, I'm going to go back and compute the score and every one of those samples, and the optimum is the best score I can get. And that configuration will give me the solution. And it seems to be very brute force, because you say, you have this high-dimensional space, you're going to sample the space, and then you're going to compute the best by computing the values everywhere. Why not, go back and simulate how this thing will assemble? And I feel the iterative approach might work sometimes, but this other approach is guaranteed to work all the time. Yet it has a high cost. So the best thing is come up with faster methods and accurate trade-offs so that I can solve the problem with some guarantee. And so that's the approach that I will be taking. So in general, for the case of n components, predicting this and finding that complex which maximizes the score in a optimization is a hard problem, just because, as I'll show you very soon, these scoring functions are highly non-convex. And so they can have multiple minima and multiple maxima. And so to find the global maximum is where the challenge lies. And so what we tend to do is we solve it in somewhat of a weak sense. We're saying, while this is highly non-convex, I'm going to give you an approximation where I'll give you k such solutions. But I'm also going to do one other thing. I'm not just going to give you the top k solutions in my algorithm. I'm going to give you some kind of a bound. How good is what is the confidence I have on each one of these solutions? And that's where the uncertainty quantification will come in. In general, the search space is huge. It's n times L. If there are n components and L are the degrees of freedom, this can become 100 to 1,000 dimensional space. So you're working very high dimensional spaces. So even for pairwise interaction, one can start to bracket the space. So before I do n to be any large number, let me take the case of n equal to 2. So in n equal to 2, you say, what are the possible transformations that I can have for two molecules such that I can go back and define what's the dimension of that space. And if I treated these two molecules as rigid, then it's well known that between two rigid molecules or two rigid objects, what are the relative transformations of one with respect to the other is a six-dimensional space. So one way to think of that six dimension is to fix one object, say, at the origin, and move this one relative to the other. How do you move one object relative to the fixed object? You can translate it in 3 dimensions, so that's 3 degrees of freedom, and you can orient it in 3 dimensions relative to this fixed orientation, and that's 3 other dimensions. So that parameterization we normally will call something like SO3 and R3. R3 is the space of translations, and SO3 is the special orthogonal group, which is capturing the space of all possible orientations in 3-dimensional space. But is that the only way? And the answer is no. For efficiency's sake, and I'll show you a little later, a better parameterization of characterizing these 6 dimensions is the following. You can think of this molecule as located, but it can orient itself. It's got 3 degrees of orientation flexibility. So can you think of this molecule? It has 3 different orientation possibilities. So 3-dimensional and 3 dimensions. But if I took the line joining their 2 centers of these 2 molecules, then there's one orientation around that axis which is common. So they're not 6 independent degrees of rotation, but really 5. And the distance between those 2 is the additional degree of freedom. So essentially, the 6 dimensions are 3 dimensions called SO3, 2 dimensions because one of them is dependent, the rotation about this axis is dependent on this orientation of this, and the distance between the 2. So this parameterization is called SO3 times S2 for the sphere and R for the translation. And why am I making a big deal of this? Because in the back of my mind, I'm thinking of efficiency. I've taken this brute force approach of exhaustive search in optimization, and I have to go back and reduce all the time, right? And I'll show you how that makes a big difference. So in general, if you have n components, the combinatorial nature of it starts impacting you. So you have 3L plus 6, where if these molecules were flexible, which I'll show you one model of it, then this thing becomes n to the r n to the l. Now symmetry will always reduce your state space, just because the number of copies, the number of n are the same, so there's a reduction in n, and there'll also be a reduction in L because many symmetric configurations can be analyzed in the same way, right? And of course when L is rigid, then of course you're down to only 6 dimensions space. So how does one go about with this kind of a quick background in coming up with a prediction algorithm for predicting even pairwise molecular binding, or we call it molecular recognition? So the goal is, I've given you 2 molecules, and I want you to tell me exactly the configuration where these would bind with highest, in some sense, binding affinity, or by highest maximum scoring function, the scoring function that we will be talking about. The scoring function I'm going to use is a biophysical scoring function. It's essentially that. I'm also using some knowledge-based potentials, but this is something called the free energy of this molecule. It's a thermodynamical biophysical model. It says, if the free energy of this molecule and the free energy of this molecule, if I had them together in a complex, there's a free energy of this complex. And if the difference between the free energy of the complex minus when they are independent is largely negative, then these 2 molecules are better off being together because everyone is trying to minimize their free energy, right? So if this delta E, which is the difference between when they are together and when they are apart, is strongly negative, then you are clearly these 2 have high affinity to each other. And that's the method that we're going to use. But how do we mathematize this is part of our goal, and then how do we make it computationally efficient? So we come up with something called an affinity function on a molecule. And so what we are going to look at is the product of these two affinity functions. One and the other one a relative transformation, either rotations or translations or some mixture of this other affinity function, and we're trying to maximize this integral over all possible points in three-dimensional space. So the optimization problem in this mathematical framework is set up as find the transformation which maximizes the scoring affinities between molecule A and molecule B under all possible motion samples or all possible transformations, right? So one way to do this is the following. Saying, let me take molecule A and define a certain affinity function purely based on, say, their complementarity. What does it mean by complementarity? As we later on understand, is something called van der Waals interactions. Two objects will come as close together as possible, but not too close till they interfere. It happens also with atoms. Atoms have a nucleus and they have electrons surrounding them. Another atom has a nucleus which is positively charged and it's balanced even with the neutral atom with all the electronic charge which is exactly equal. So neutral atoms have electronic clouds, and the electronic cloud is attracted by the nucleus of a neighboring atom because positive attracts negative. Similarly, the nucleus of this other atom is attracting the electronic cloud of this one. But as they get closer and closer together, the electronic clouds start interfering. So there's this both pull and push phenomenon, and there's a stable point. And that's, the fact of not two objects can come too close together, and they want to come as close together as possible because of this attraction pull, but then this is repulsion pull of the electronic clouds. This is the same principle, what we call van der Waals forces between even molecules. So two molecules will try to come as close together as possible, but not interfere with each other. And so in this case, I have this molecule A, and I'm saying, let me put a little skin around this molecule. I'm just calling it a skin. It's a little layer of how close I can get this molecule to. And this molecule, I'll take the first layer of atoms surrounding it as a skin. So the green colors are the skin, and the reds are the remaining what we call cores. And now I'm going to define a very simple mathematical function. It's a complex function. I'm saying skin have a real value, and the core has a complex value. So it could be 1, and this could be I, square root of minus 1. Same thing, skins have 1, square root of minus 1. Now if I take the product of these two complex functions, real will give me a real. Real complex will give me a complex. Two complexes multiplied together give me a negative real. I squared is equal to minus 1. So this is in some sense, the product is mimicking the fact that if there's real interaction, there will be a high real score. And if there's a conflict between the imaginary and the real, that will give me a complex value. And if a complex interacts, that will give me a negative real. So if I take the sum, which is the integral of this product, then I'm actually getting this behavior that I'm trying to mimic. I want these two molecules to come as close together such that it maximizes their skin-skin overlap and minimizes their skin core or core-core overlap. So they shouldn't interfere together, but they should come very close to minimize the van der Waals forces. So such is the methodology that we adopt in capturing the thermodynamical term of our free energy and mathematizing it into a very simple, integral of a product of functions. To show you this is just a little movie to show you how molecules spontaneously come together to minimize their free energy. So the model that I've been adopting, as Alexei and several others, has been the thermodynamic free energy model, which contains of two terms, actually contains three terms. It's got the molecular mechanical model for the molecule. This is the interaction with water and this is the entropy contribution. So molecules by themselves are bonded, and as they flex and change conformations, there's an energy which has both bonded energy terms of stretching and flexing, as well as non-bonded interactions, just because there's something called partial charges on each one of them. As bonds are created, charges shift. Hydrogen becomes positively charged and oxygen becomes negatively charged in different extents. So such non-bonded interactions are quadratic in nature, and the van der Waals force that I was telling you about was this one, this term of no two molecules come too close together, or they can't be, they want to be as close together as possible, but not too close. And the fact that sometimes when you start to look at this, say, why is this r to the 12th and r to the 6th? These are empirical fitting curves that model this kind of behavior that people have observed in experiments. And there's a lot of activity that biophysicists do in coming up with these appropriate constants so that pairwise atomic interactions, because the nice thing about organic is you're mostly working with a finite number of types of atoms, carbon, nitrogen, oxygen, maybe a little bit of sulfur and phosphor and so on. So you can take all these pairwise interactions and adjust these curves so that you get as close to the real energy as you observe. The more complicated term, though, is not the internal energy of the molecule, but how the molecule interacts with the water. And in this implicit solvation approximation, there's been two kinds of theories of capturing that kind of interaction. There's both a area and a volume dependence, and then there's something called dispersion, but there's this very complicated term called polarization. And this is what adds a lot to the non-convexity of biophysical interactions, and what makes this a grand challenge problem. Otherwise, it would be a very simple, quadratic optimization or something like that we have developed lots of tools to solve. So this one requires actually the solution of a differential equation. And this one is somewhat of a complicated summation, which is more than n squared. It's something like an n cubed behavior, because each term has to be approximated by an integral. So a lot of work has gone on in making these algorithms efficient. And how do you do generalized norm calculations in less than n squared time? So in linear time, linear in the number of atoms. Or how do you solve the Poisson-Boltzmann equation in linear time? Because if you can think about this, this is all in the inner loop of my search. I have to do this for every configuration. This is configurational dependent. This is depending on the position of every atom in my molecule. So I'm going to rotate this molecule, all of the positions change. And I have to recalculate this integral. So being in the inner loop, it behooves you to first make sure that that's the fastest you can do. Again, with bounded error. And then, of course, you're trying to optimize the combinatorics, the large search space that you have to calculate this optimization over. So we spent a lot of time on working on this, as has Alexei, as well as the student who's going to give, Boris, who's giving his PhD defense today, is actually also giving you a fast algorithm with accuracy trade-offs as generalized. Now, what makes the problem even harder is the fact that molecules are flexible. And this flexibility is another grand challenge problem for computational biology. Given a structure, maybe elucidated by X-ray diffraction, can you tell me how flexible this is going to be in its native environment? Because a crystallized structure is an idealized environment, but can you now predict? And this is where molecular dynamics has tried to answer this question. But again, in trying to develop an alternate pathway to, this little simulation here is something that we did with our Poisson-Boltzmann calculation. This red is negative potential, blue is positive potential. And you can see there's a cancellation of these two molecules' potentials when they come together. These potentials are far-reaching. They're like gravitational pulls. You can think of this, this asteroid or this other planet trapping a space vehicle in its gravitational potential, and it sucks the thing in. And this is similar, except that here, gravitational pull is a single positive value in some sense, and here you've got positive and negative, So positive potentials attract negative potentials. So if a molecule has a strong negative potential, it'll get quickly sucked into a positive potential field. And that's the nature of why these calculations are very important, because the contribution for these terms are, a large percentage of the overall free energy of interaction. This flexibility problem is a, not only one PhD, but I think several dozen PhDs work, because progressively, as we build upon prior work in the shoulders of, giant predecessors, we are constantly understanding a lot more about how certain prediction techniques of flexibility are in some sense, can be improved upon. Efficiency is my big thing, but accuracy comes before efficiency for me. And I like to look at accuracy, efficiency trade-offs. So one thing is that if I was to think of this molecule as a bounded chain which folds itself, then roughly there are 3 times the number of bonds, degrees of freedom. So if I'm working with a 5,000 atom model of a molecule, I've got now 15,000 degrees of freedom if I'm going to do the full, flexibility. I said, oh, wait a minute, I had assembly problem with, say, 100 proteins, and now I've got 15,000 dimensional spaces. Again, it's exploding my entire problem. So what we tend to do is dimension reduction. Say, can I come up with reduced degrees of freedom, which are the essential degrees of freedom, and at least find a feasible solution there? And then progressively, I'll increase the degrees of freedom and find other feasible solutions as we go. So one way of doing dimension reduction is the following. Saying, let's take any knowledge we have about how groups of atoms move together. So if it's like a flap in the molecule or a loop, it moves, a collection of atoms moves together. And if this thing folds like an antibody, it's got 2 arms which are flapping. So the large groups of atoms are moving together. How do we recognize these domains? Well, there are several techniques. You can do molecular dynamics, you can do what I call principal components. You can do something called normal mode analysis with the weakened energy functional. Or you can use some domain knowledge. Oh, this is a molecule which is an antibody. We know antibodies have these 2 flappable arms. And so we can identify these domains. So once you've identified these domains, you go back and say, what is the interdomain motion that is feasible? And we call that a motion graph. So like in this molecule, there's a core domain, there's something called an AMP binding domain, and then there's a lid domain over here. And so we work out the possible motions between these domains, encode them based on their interfaces, and come up with different types of either translation or shear or twisting or rotational. So we parameterize the entire molecule into a motion graph, which is again parameterized by translation R3 or translation R2 or rotation S2 or rotation SO3 and so on. And so then once we have that, we can go back and sample all of these reduced degrees of freedom by sampling those SO3s and S2s. So that's the exercise we are currently doing. Not to say that this is the best thing, but progressively we can go back and then factor each domain into its internal degrees of freedom and perhaps come up with an improved model of prediction based on increasing the search space. So now coming back to this pairwise docking, and I'll just tell you a little bit about why parameterizations of motion are so important. So remember this integral I have to calculate. And this integral that I have to calculate is, summed up over all possible configurations in motion space, which is 6-dimensional, even for rigid objects, and higher dimensional. And furthermore, it's a product in the spatial domain of 3 dimensions. And when I look at this, I say, oh, this is very much like what is called a convolution integral. It's taking a function, transforming another function, or shifting it by some transformation, and taking the product. So such convolution integrals, naively, is going to be very expensive to compute. can I improve on it? And says, oh yeah, we've learned something called Fourier transforms. And Fourier transforms help you speed up convolution. The only distinction is this Fourier transform is over motion space. It's over the space of transformations. So you're now doing Fourier convolution integrals over motion space. And how do you optimize that? Well, here's one way. So even 3D rigid body docking, when you're solving this, you say, I'm going to use the discrete Fourier transform. And if I was being very naive, that's what level 0 means, I would just take the product, and if I have m samples of my motion space and m samples in my translation space, totally, I'm sorry, m cubed samples here and m cubed samples there for each of the dimensions, I would have m6 samples, and I'll be computing the product of the sizes of all of them. So the naive approach for m cubed translations and m cubed rotations would be a times b times m to the 6th. This is by parameterizing rigid body motion as 3 degrees of translation and 3 degrees of rotation. We're saying, oh, but I know about the Fourier convolution theorem, so I can go back and approximate this by a Fourier sum and use discrete fast Fourier transforms. So I can reduce this complexity by an m cube. Why only m cube? The reason being, I have to choose now. Is my coordinates for my Fourier transform the basis? Is it over translation space or rotation space? I have 3 dimensions of translation and 3 dimensions of rotation. They're different parameters. So when I express my Fourier, convolution integral in Fourier basis, I have to choose the right basis. So suppose I take translations, then I have 3 degrees of freedom there. Suppose I take rotations, I have 3 degrees of translations there. So I have to make a choice. I can't do both simultaneously. And so, hence the best reduction I can get is something like m cubed times the size of a plus b plus m cubed. So, for the purest computer scientists and users, saying, oh, this is still m to the 6th worst case complexity, but the constant in front of the m cubed is much, much smaller than in the case of m to the 6th. Or the constant in front of the m to the 6th is much, much smaller now. And so this does make a big difference. But it's not the ultimate. What's the ultimate? Saying, the more I can put my degrees of freedom into the same space, then I can optimize over that same coordinate system. So if I had 5 degrees of rotations, I can then do Fourier convolution integrals in 5-dimensional space and get a reduction in 5-dimensional space. Now how do you do that? It requires going back and expressing what I call spherical Fourier series. But you recall that this was not homogeneous 5 degrees of freedom. This was 3 dimensions for one molecule, 2 dimensions of rotation for another molecule. So there's a little bit of math jugglery that you have to do to make this all work out. And that's defined by using both spherical harmonics as well as something called Lagrange polynomials. I'm not just wanting to, throw this math out to you, but I'm saying that this math that we learn has some real good use. And the computer scientists in us recognizes the fact that while the mathematicians have worked out this, you can go back and actually solve this problem if you had chosen the right parameterization. So this is something called Wigner-D basis functions that allow you to do everything now, and you can get a reduction of m to the 5 in your complexity just by doing this calculation. There's one other complexity that we have to worry about. Most of the time we learn about Fourier transforms, which are called uniform Fourier transforms. So uniform, we take a grid, and then we do the convolution integrals over a grid, and there's uniform spacing. That's where the fast Fourier transforms have been developed. But in molecules, we get this extra challenge. Atoms are not on a regular grid. They are all scattered in space. And we are doing this motion sampling also when scattered in space. And so we have to resort to something called non-uniform fast Fourier transform. And so that's another thing where you hit a challenge, you go into the math, and you say, oh, I can actually take the uniform Fourier transform and develop a new non-uniform approximation, which I can harness back and bring back. And that's the kind of work we've been doing. So with that, let me hit the next key problem, because this is, when we solve these other problems, then we can put it all together into solving our prediction problem. The next big problem is, how do I sample space? Now, sampling translation space is easy. When I say sampling, I want uniform sampling. And what I mean by uniform sampling is I have a certain number of samples I'm going to use, n. N can be 1 million, n can be 10 million, depending on how much firepower I have, because I want to solve things within my time frame that I want to go back and succeed. So we choose a number of samples that we're going to discretize this over. And say, I want to make my sampling most effective. I don't want all my samples in one crowded corner of this high-dimensional space. I'm going to leave large gaps somewhere. So how do I choose samples such that I get a uniform distribution of my entire space, such that I have high confidence that the optimization I'm doing over this high-dimensional space is the true optimum? Because if I crowd it in one corner with all my samples, the optimum could be lying somewhere else. So there's this notion of what's called low discrepancy sampling. And low discrepancy sampling is a nice computational trick or a measure which allows you to develop what I call deterministic algorithms to do the sampling with guarantees. So the problem of sampling a three-dimensional solid sphere is not easy. Also the sampling on a sphere. You say, take a sphere, how do you put samples on a sphere such that the distance between every two samples is equal? In a grid, of course, it's very easy. You can just take uniform samples along each dimension, and that grid, the distance between every two pair of samples is exactly the same, right? Or bounded. I mean, along the grid, it's 1, and along the long diagonal, maybe square root of 3 over 2, but it's bounded in some sense. There's no large gaps. But to do this in the solid sphere was one of Hilbert's problems back in early 1900s. He says, how do you sample within a solid sphere? And this is really a solid sphere in 4 dimensions. So that's what the space of orientations in space is all about, or the SO3 spaces. Now, to come up with such solid sphere samplings which are uniform, one resorts to something called this low discrepancy. So what is discrepancy? The actual measure is this little thing here, but you can probably see it easier by this little figure. So if you're trying to get samples, you define a family of subsets. And so here the family of subsets that I'm going to define are all subsets of little slices of the sphere. This can be this small or larger and so on. So say, take a measure on these subsets and you find that if the number of samples that are in any subset divided by the total number of samples is roughly the same as the area of this subset time divided by the total area. So if the number of samples that you have, if you take a big area, you need many more samples, and if you take a small area, you need small samples. And if these two ratios are equal, then you've got zero discrepancy, you've got pure uniformity, right? Also, you don't want too many large gaps. That means every time I look at a thing, I must have some number of samples here. So dispersion and discrepancy are very much related. So it's a very common measure. Say, every time I look at any region of space, and I'm going to do this for all families, and I say, take a big subset, the number of samples in that big subset divided by the total number of samples is roughly equal to how big is that subset divided by the whole. And so if you've got that, and you've got low discrepancy, that means there's no difference between the volume measure and the number of samples cardinality, which is what is shown here, then you've got uniform sampling or low discrepancy bounded sampling. So this has been a lot of research, and especially for high dimensional searches, and is also the guts of what people do in data mining, or the big data problem. So when you're solving for large data, how do you sample this large data? And if data could have many parameters, how do you come up with good low discrepancy sampling so that you have enough confidence that you have not left large gaps anywhere? So sampling is kind of a key problem, and it's of course a key problem for our prediction because we are working in searching in these high dimensional spaces. So this is some of the work that I've been also doing with 2 other students of mine and another faculty member called David Zuckerman, Bhavik and Chandrajit, in coming up with good algorithms for sampling which are deterministic and also have very low number of samples with bounded discrepancy. So just to give you an illusion of a nice problem that comes in backbone sampling of molecules and also side chain sampling for confirmation for the folding problem, you can say, if I had a backbone in a molecule, then I have really what is called a product space. It's called SO3 to the N. Each torsion angle has 3 degrees of freedom, say, and if they have N bonds, then it's a product of those samples. And naively, what would you do? So naively, you would say, oh, let me take each torsion angle and sample it uniformly with low discrepancy, having solved Hilbert's problem. And for the product, I'll just take the product of all uniform samples. But the number of samples I will get is 2 to the product, because, or I should say, m to the product. So if I take k samples or m samples in each SO3, and if I have a product chain of m, then I'm taking an exponential number of samples. I'm going to take m's uniform samples, and I have to take all combinations of them. Such exponential number of samples is too large. So what we've been doing is coming up with what I call, polynomial number of samples, and this is done by a nice trick called pseudo-random number generators. And pseudo-random number generators, as you know, are deterministic sampling methods, which have good randomness in them, but they have also what's called bounded discrepancy. So one can prove that there's an efficient deterministic sampling of n points in this product space with discrepancy bounded by epsilon with respect to cross products of local Cartesian convex sets, where n is not exponential, but it's n to the epsilon times log of 1 over epsilon. So if you make epsilon smaller and smaller, you want uniformity within epsilon, then the number of the polynomial will be of higher and higher ordered exponents. So given this, our next goal is, how do we use this in our pairwise docking? And the goal there is to go back and take this docking and apply this with deterministic sampling, do this convolution with fast Fourier, and come up with scores. And then when we do this, we normally take benchmarks of known complexes, take them apart, and try to resample them. And so this way, we can go back and try to make predictions. But this is what I was doing several years ago. And we published several papers. In the back of my mind, there was always this thing. When I do predictions with a known sample set, or a known set of benchmarks, where I take things apart and try to predict them together, I can check my errors. But will it really work in practice? Do I really have a prediction tool? What confidence do I have that it will really work on an unknown data set? So this is where uncertainty comes in, and uncertainty quantification comes in. And so what we say is, normally what we do is we do validation, where we go back and check if our model is capturing the reality. We're also doing verification of looking at the numerical accuracy. But we should also start to now do uncertainty quantification, which relates to both. So what we mean by that is come up with a certain certificate of saying how far is my prediction from the true solution, to the true solution. There are many types of bounds, Hofding bound and Chernoff bound, which has the following flavor. Can you prove that probabilistically my prediction, the distance away from a certain value, is bounded by some epsilon? So a certificate for the overall mathematical and computational model, which essentially guarantees that the probability that the solution that you're providing does not differ from the correct solution by more than a given threshold, is always very, very small. So the user can choose this epsilon, and then I have to work hard in saying how many samples do I have to take such that I can meet this bound. So that's the nature of uncertainty quantification and prediction. And given the time, and I think we started a few minutes late, I'll skip some of these slides of how we go back and compute this uncertainties for the set. So I would like to end up and show you at least the key ideas now of all these pieces that I've done and how I've gone back and put this together into this assembly problem in the next remaining 10 minutes or so that I have. So the 3D flexible assembly problem has, besides the pairwise interaction, an additional combinatorial. What is the correct arrangement that I have to solve? So it's a combinatorial plus geometric optimization problem that we have to look at. And so we can come up with one way of saying, suppose we have a good way of looking at pairwise interactions. And if we have done bounded uncertainty for pairwise interactions, can we use this now for bounded uncertainty for 3D assembly or even symmetric assemblies? So we go back to our original problem and we define something called a multigraph. What's this multigraph? We take each component and we think of it having an edge and multiple edges. And let's take a k number of edges. And these k number of edges are the k top-ranked solutions with high, with the best Chernoff bounds that I've computed for pairwise interactions. So I'm saying I can't solve this thing optimally, but I'm giving you the k best solutions of A and B interacting with C, A interacting with C. And what am I interested in? I'm interested in what's called a spanning tree of this multigraph. What's a spanning tree? Because as soon as suppose I was to pick one configuration between A and C, and another configuration between B and C, then I've locked in the configuration for A, B, and C. Because as soon as I've done AC and BC, then AB is automatically determined. So I don't really, in this graph, I just need a spanning tree. So the problem statement can be, given this assembly graph, which is a multi-graph, report a spanning tree which has the highest scoring of my assembly. So the multi-protein problem, a version of that can be formalized in this way. This problem is hard, and it's provably NP hard, and a very simple version of this 2D problem is called the monkey puzzle problem. That you're given only, say, some n pieces, n by n pieces, or square root of n by square root of n pieces, and each piece has a pattern on it, and you want to come back and put this thing together such that in the correct assembly, the monkeys are complete, right? And so what people have shown is they can reduce well-known NP hard problems to this problem. And even for this special case of n puzzles, this problem is NP hard, it's not even NP complete. It also has what we then tend to do is develop what are called PTAS, polynomial time approximation schemes for solving this problem. And so we borrowed from that, and just to give you a flavor of why this problem is, is a hard problem, is the obvious method or the greedy approach will not work. So suppose you had these three components of this puzzle, and you had these certificates and scores which are labels showing us edges. And you say, oh, let me take the best one between A and C, that's 12, and the best one between B and C, and that's 12, and therefore I will look at the final score that I get. So in this algorithm, which was done by Inbar and Wolfson and so on, when they published, they used a greedy approach and said, at least I'm giving you a prediction for a multi-component problem. What they do is they construct these spanning trees greedily. They start up with singleton nodes, and they add the best possible configuration for every pair, and they keep a finite list of them. And this is the D top scoring subtrees until they go back and complete. But as you can notice, the best scoring gives you this configuration, which is 24 as a score, but that's not the correct solution. A better solution is not to be greedy, but to widen your search, because clearly the best solution here, which is ABC, required that AB take a weaker score and BC take a weaker score, but the sum of all these three scores is actually the maximum. So hence greedy approaches don't work, and you have to use kind of prudent search methods to go back and solve this problem. So this is what my previous student did, and we defined this program called Flexemble. So this has many characteristics. It has less bias and more robust to false starts. We use uncertainty quantification and z-scores in our determination of what are the correct subtrees. We actually add some weights. There's lower false positives and lower negatives, and so on. And so, again, is this the ultimate prediction algorithm? Answer is no. I'm giving you a certain bound and a certain complexity, but it's not really there. So there's much more work to be done yet on this. So again, in the interest of time, I'm going to skip through some examples and come to this symmetric assembly in the remaining 5 minutes that I have. So viral capsids has been always an interest of mine for many, many years as I've been learning biology slowly and incrementally. And it's this sheer nature that you can get these myriad of patterns on viruses. Not only do they form a single shell, sometimes they form double shells. So this is well-known rice ball virus that is very virulent and destroyed lots of rice plants, and an antidote had to be found for, or a way to defeat the life cycle had to be found. But its geometry is very alluring. The outer shell has a very large complexity. It has something like 780 copies of the same protein. And the inner shell has another arrangement. It uses only 120 copies. And these two proteins are different. This is called B8 and this is B7. And the fact that these things happen spontaneously is the other miracle that one has to look at. So I'm not going to consider the complete dynamics of spontaneous assembly. I'm just trying to figure out whether I can predict these kinds of assemblies. Now, way back in '62, 2 Nobel Prize winners, Caspar and Ploog, came up with this theory called the Caspar-Ploog theory. They said, let's look at an icosahedron and the special case of icosahedral symmetric viruses. And for these viruses, you can come up with a planar unfolding. An icosahedron has 20 equilateral triangles. And if you fix one triangle, then you can, of course, tell you the entire tiling of that icosahedron. And an equilateral triangle, if you fix one edge, then you fix the entire equilateral triangle, because equilateral triangle has 3 equal edges and 60 degrees on each one of them. And the best way to lay them out is on a hexagonal grid. They call it the HK grid. And you can also get subdivisions and other kinds of complicated triangles. And so this T number, which is h squared plus k squared plus hk, is a regular tiling using the same element. And the larger the T, the larger was the virus's complexity. The more proteins it was using, copies of the protein to build bigger and bigger shells. And people have discovered now viruses which have T numbers of 2,000 or even more. And so this is something which is amazing, that such stabilized structures also can self-assemble. So this is an example of how the T number does in Caspar-Ploog. It has what I call only a few ligaments. But Caspar-Ploog theory doesn't work all the time. There are many examples, and there's this one on the polyoma virus that cannot be done by a regular tiling. So to cut the long story short, you take a gander or take a walk across and start looking at tiling theory, and that's another very richly developed theory. And the bottom line is that there are many possible types of tilings. There's crystal symmetries occurring in tilings, and there's quasi-crystal symmetries occurring in tilings. And there's something called regular tilings, and something called semi-regular, and then something called aperiodic tilings. And funny thing is, they occur in nature. So what we determined through all of this learning exercise is that if I have to come up with a prediction algorithm, I cannot only look at Caspar-Ploog tilings, I have to enumerate also all kinds of aperiodic tilings and search over them to find the right answer. So again, skipping some of these subdivision things, let me give you this gust of the algorithm that we've implemented and have worked on. So what we do is, it's a 4-step algorithm. We enumerate all possible regular, semi-regular, aperiodic tilings. So you can go back and come up with a myriad of layouts of different types of what we call layouts of an icosahedron or of a sphere. So an icosahedron, since there are 5 platonic solids, you can think about sphere tilings are all by looking at the base polyhedron, one of the 5, and consider subdivisions of that polyhedron, and they give you similar mappings on the sphere. So once you know you pick one of these layouts, and since these are finite in number, you go back and take your building block, your primitive protein, and come up with different types of cyclic configurations in which they are stable, using your pairwise docking algorithm and your multi-protein docking algorithm. And so you come up with the best top rank with the best Chernoff bounds for each one of them. And then you put each one of them, you decorate them on your tiling, and find global consistency of the decoration. So what kind of cyclic configurations do you need to explore? Essentially twofold, threefold, fivefold, sixfold, and that's enough for most of the spherical tilings, both aperiodic and periodic. And so these are again finite in number, the layouts are finite in number, and the search then is over this consistency check, which is polynomial in the total number of possible rearrangements. And to conclude, let me show you some examples of our successes, also of some failures. So in this very simple case, we can predict, our top rank solutions predict something that is very similar to what nature's solution is, but in some cases it predicts other kinds of assemblies which are not that close to the final solution. But part of the nice thing about computational biology and prediction algorithms is you can start predicting many, many other things. And possibly they don't occur in nature, but they can be used for perhaps our design purposes for other kinds of nanostructures or even macrostructures later on. So in the Rice dwarf case, which was 22,000 atoms, our top two scoring models showed this one had the same chirality and the same layout and similar oligomers to nature's Rice dwarf virus capsid, and this was given from an X-ray model. But the diameter that we predicted was about 0.9 less than the X-ray model, showing that our affinity functions are really not capturing everything, and neither is our flexibility. But then comes this other case that this is for the other the outer shell, but here's the final set of examples. In the case of the same protein, we can predict also stable structures which are t equal to 3. Recall this is the outer shell, and t equal to 3 is not stable because there must be pressures from the inner shell as this outer shell is being assembled that says, even though this is a stable structure, at least mathematically, this is not the final structure that is being produced. And this one is closer to the one in nature, but then we can also predict in higher t numbers, even though nature does not do that. I can predict t equal to 49, I can predict t equal to 100, and I can also predict t equal to something in the thousands. So the more steps or the more finally you make the layouts, the better off you become. So finally, I'll leave with this final slide, is our work going forward is to go back and produce these by using what I call uncertainty propagation, come up with true Chernoff bounds on our full prediction models. Because not only can I capture from nature's models, but when I'm predicting things which I can't observe, I have no way to experimentally validate, I at least want to come up with a theoretical certificate of saying, well, I'm this much sure that my prediction is not that far away from the true solution. So with that, I'll stop and take questions, and sorry to run over a couple of minutes. Thank you very much.
Questions? Let me start this final slide with several virus predictions. So I'm wondering, it's known that, at least for some viruses, depending on the slight variations of external conditions, you can have them assembled in slightly different shapes.
That's right.
So I wonder if your predictions are actually correspond to something that exists under slightly different conditions. Could they be sort of alternative assembly?
Yeah. I think what you're getting at is something I was also looking at, which is the pH-dependent swelling of these viruses, right? In our scoring functions today, we don't take the pH into account. It's all done at constant pH, right? So even though we are taking solvation effects, it's all at constant pH. But what you're alluding to is something definitely that can be added to the prediction. So if I was to change the pH level, I would change the scoring function, hence I would predict many different configurations. And some of these other sizes which are stable will start coming up in that case. But very good. Yeah. Currently we're not doing it, but this would be a good thing to add. Yes, go ahead.
So you you showed this picture where you had these potentials around
Right.
the surface, right? So I was wondering, why not, if you have red and blue right on top of each other, they're more likely to be bound. So when you're sampling, why are you not sampling based on the, how strong the potentials are, based on the potential in the scoring? So,
What you're pointing out is something that we do.
oh, you,
I did not mention it, but clearly the sampling, when I said low discrepancy, you can do what is called low discrepancy adaptive sampling or bias sampling. So you can bias it by different charge functions. Also, when you're searching, I'm not searching in all of the space. Normally I'm searching in a certain shell surrounding the other molecule. So such sub-range biases can be made. And you can do block-based or bias sampling. But within that block, you have to do guaranteed low discrepancy. But very true. Other questions? Yes,
Another question. So one thing that intrigued me a lot was the error bound.
Uh-huh.
And so I could see how you can put error bound on something. One thing that intrigued me a lot is that your function, your physics function, right? There's no exact solution.
Mhm.
So how do you work in the uncertainty of the function into your error bound?
Okay.
How does that work?
So there's two things there. So if you look at your function itself, so one function could be, let's take the van der Waals function, right? Its uncertainty is propagated from the uncertainty in the position of each atom. So some of the slides I skipped captured this. So if for a crystal structure, you can take the temperature factors, compute a variance on the position, percolate that to the molecular surface, and then use that to estimate the variance.
Quickly show you, this was exactly the slide.